To solve a linear system of equations using the elimination method requires trying to get rid of one of the variables by adding the equations together. Now, to try to get rid of a variable, what you really want to look for are, in your two equations, the same variable in both equations that have the same coefficient with the opposite sign. And by coefficient, I mean the number that's multiplying your variable. Our first equation is negative 8x plus 3y is equal to 7. Second equation, 13x minus 3y equal to negative 17. You might notice that our variable y in both the equations has the coefficient of 3. However, one is positive and the other is negative. This is exactly what we like to see in our two equations to set up use of elimination. Now, you might also notice that both of our equations are written in standard form, where you have both variables and their coefficients on the same side of the equation and a constant on the other side of the equation. Usually it looks like some number a at times x plus some number b times y is equal to some constant c. You'll notice both of our equations are in that form. This is the best way to write your equations so that you can most easily use the elimination method. So since this is the perfect example where we can easily eliminate the equations, let's go ahead and add our two equations together. Now, when we add equations together, make sure that you are only combining the like terms. So only add the x values with the x's, the y's with the y's, and the constants with the constants. So we'll start with negative 8x plus 13x, which is going to give us 5x. Now this is why we wanted to add these two equations together and use elimination method, because when we add a positive 3y with a negative 3y, they give you 0y. So the variable y is eliminated from our equation. Finally, we just add our two constants together. 7 plus negative 17 gives us 5x equals to negative 10. Dividing both sides of the equation by 5 gives us the value for x, negative 2. This value for x will make both of these equations true, and we can use it to help us find our value for y by substituting into one of our original equations. You can choose either of the two equations to substitute x into, so I am going to choose the first equation, negative 8x plus 3y equals 7. But instead of using x, I'm going to use the value it's equal to, which is negative 2. Negative 8 times negative 2 gives you 16 plus 3y equals 7. Subtracting 16 from both sides leaves you with 3y is equal to negative 9. And finally, dividing both sides by 3 leaves you with the value y is equal to negative 3. Now, we need to go ahead and check that these values are correct and solve both equations. So let's substitute them back into our original equations and see if they're true. Plugging the values back into the first equation, negative 8 times negative 2 gives you 16. And 3 times negative 3, the value for y, gives you negative 9. 16 minus 9 does indeed give you 7. In the second equation, 13 times negative 2 is negative 26. Negative 3 times negative 3 gives you positive 9. And when you add these two values together, you do get negative 17. Our solution to the system gives us true statements for both of our equations. In this system of equations, we have 9x plus 6y is equal to negative 3, as well as 5x plus 6y equal to 9. Now you might notice in this situation, y values once again have the same coefficient, but this time they don't have the opposite value. So what you might sometimes need to do is multiply one of the equations by a number to make it work for our elimination method. In this case, what we want to do is have a negative 6y in one of our two equations, so that way when we add our two equations together, they are eliminated. So what we can multiply one of our equations by, and I'm going to choose the bottom equation here, second equation, though it doesn't really matter, I'm going to multiply it by a negative 1. Now let's rewrite our equations to see if we can now add and eliminate. Our coefficients for y have the same value but the opposite sign, so we can go ahead and add our values. 9x minus 5x gives you 4x. 6y minus 6y is eliminated. And negative 3 plus a negative 9 gives you a negative 12. Dividing both sides by 4 leaves us with x is equal to negative 3 as our x value. Substituting that value, negative 3, for x in our first equation will let us solve for y. 9 times negative 3 gives us negative 27 plus 6y is equal to negative 3. Adding 27 to both sides gives us 6y is equal to 24. And finally, dividing both sides by 6 leaves us with y is equal to 4. Once again, we can check our work by substituting the values negative 3 back in for x. In the first equation, 9 times negative 3 gives us negative 27. And our y value in for 4 for y, as 6 times 4 is 24 here. When we add these together, we get negative 3. 5 times negative 3 is negative 15. 6 times 4 is 24. Adding these two values together gives us 9. So our equations are both proven true. Now in our next example, you will notice that our two equations, negative 3x minus 4y equals negative 22, and 2x plus 5y is equal to 17. Neither one of our variables has the same coefficient in both equations. So what we're going to have to do is multiply, in this case, both of our equations by a number to try and eliminate one of the variables. Now in this case, we can choose which variable we want to eliminate. I'm going to choose to eliminate the variable x. Now, to do this, to try to eliminate the variable x, I want to come up with the coefficients for both of these equations should be the least common multiple of 3 and 2. One of the simplest ways that you can multiply your two equations to make sure this happens is to simply multiply one equation by the other coefficient. I'm going to multiply this first equation by 2, and the second equation I'm going to multiply by 3. That way, when I multiply 2 times negative 3x, I get negative 6x. And when I multiply 3 times 2x, I get positive 6x. Meaning that when I add these two equations together, the x variable will be eliminated. But we have to multiply these numbers with all three of our terms in the equation. So 2 times negative 4y will give us negative 8y, which will be equal to 2 times negative 22, which is negative 44. Same thing happens in our second equation, which is being multiplied by 3. 3 times 5y will give us positive 15y, and 3 times 17 will give us 51. Now we can go ahead and add our two equations together. Negative 6x plus 6x is 0, so the variable x is eliminated. Negative 8y plus 15y gives us 7y, which will be equal to negative 44 plus 51, which is equal to 7. So dividing both sides by 7 will give us the value of 1 for y. Plugging the value of 1 back into y in one of our original equations, I always like to go back to the original equations instead of the equations that I multiplied to get, just in case there was any mistake. I don't double up on a mistake. So we can go ahead and solve for x. Multiplying negative 4 times 1 gives us negative 3x minus 4 is equal to negative 22. Adding 4 to both sides gives us negative 3x is equal to negative 18. Then finally dividing by negative 3 on both sides of the equation will yield x is equal to positive 6. Substituting the values 6 for x and 1 for I into both of our original equations will give us true results for both equations, which means that these are the solutions for this system. Our fourth example features another system of equations where we must multiply both of our equations by a number to be able to eliminate one of the variables. This time, let's choose to eliminate the variable y. Multiply our first equation by 7, so we get 5 times 7, and our second equation by 5. Multiplying the first equation by 7 gives us the equation 49x minus 35y is equal to negative 168, and multiplying the second equation by 5 gives us negative 30x plus 35y is equal to 35. So as you can see, our y variable has negative 35 and positive 35, so we can easily add our two equations together to eliminate the variable y. So 49x minus 30x gives you 19x. The y's are going to be eliminated as planned for, and negative 168 plus 35 is negative 133. Now, dividing both sides by 19 gives us the value of x is equal to negative 7. Plugging in our x value into one of our original equations, in this case I chose the second one, will allow us to solve for y. Negative 6 times negative 7 gives you 42, plus 7y is equal to 7. Subtracting 42 from both sides leaves you with 7y is equal to negative 35. And finally, dividing both sides by 7 gives us y equals to negative 5, potentially our solution for this system of equations. Once again, substituting our two solution values, negative 7 for x and negative 5 for y, into both equations leaves us with the true statements that our equation was supposed to give us in the beginning: negative 24 for the first equation, and positive 7 for the second equation. Now, example number 5 is going to give us a chance to look at what happens when elimination problems go wrong, or give us some strange answers, and what that tells us about our system of equations. In system A, you're going to notice that we have 3x plus 5y equals 9, and 3x plus 5y is equal to 4. If I multiply the second equation in system A by negative 1, and then add these two equations together, you'll notice that not only does 3x and negative 3x eliminate, but also 5y and negative 5y, leaving your one side of the equation only equal to 0. Now on our other side of the equation, 9 plus negative 4, that's equal to 5, which gives us an answer that is impossible. 0 is not equal to 5. This is a false statement. And when using elimination, or any other method of solving a system of equations algebraically, and you get this false statement, well, what that tells you is that your system is inconsistent. The lines are actually parallel, which means that they don't intersect and your system has no solution. In system B, we have y is equal to 8x and y is equal to 2x. So this isn't exactly great for using elimination method, but we can easily use substitution. Since we know that y is equal to 8x and y is also equal to 2x, we can substitute 8x for y, giving us the equation 8x is equal to 2x. If we subtract 2x from both sides, we can get 6x is equal to 0. Dividing both sides by 6 leaves us with x equals 0. And in this case, if we substitute x equals 0 into either one of our equations, we find that y equals 0 is also a solution. So in this case, the system has a unique solution. Our coordinate point x, y should be equal to 0, 0. This is where the two lines intersect at the origin in this case. In our final example, we must again solve the system of equations and determine whether it has a solution, no solution, or infinitely many solutions. So you can see in our first set of equations that the variable negative x and x can be found in these two equations. There's also 2y and negative 2y. So we can go ahead and add these equations together. Doing so gives us something a little strange. Negative x plus x is 0, so they eliminate. 2y plus negative 2y is also 0, so our left side is just equal to 0. But in this case, negative 4 plus 4 is also equal to 0. So even though everything canceled out in these equations, this is a true statement. 0 actually is equal to 0. So what this tells us is that these two equations are actually the same. They are what are called coinciding. It's two linear equations, one on top of the other. So they intersect at every single point, which means they have infinitely many solutions. Now, for this particular problem, it also wants us to find the equation that these both are equal to. And it's asking us to solve for y. So we can take one of our equations, doesn't matter which one, and solve for y. So in this case, we can add x to both sides, giving us 2y is equal to x minus 4. Then we can divide both sides of the equation by 2, leaving us with y is equal to, well, 1x divided by 2 is half of x, minus 4 divided by 2. So this satisfies the equation y is equal to 1/2 x minus 2. Our second set of equations is similar to the first set. Here we can tell that we can very easily just add our two equations together. However, this time, our left side becomes eliminated, which is equal to 0, but 3 plus 3 is equal to 6. And we know that 0 is not equal to 6. This is a false statement, which means that our system has no solution.